Hi, everybody. Welcome back. I see Musin is busy admitting more people to the room, so we'll start slow as people arrive. This is our kind of wash-up session. We have a couple of things to get through. We want to look at your designs. I'm really excited to see. I've already had a good look at everything that you have been submitting. So we'll take a look at those in a second. Then we also realized we had some technical difficulties this morning, looking at some of our manufacturing techniques and technologies and different devices that we use to manufacture. So we're going to take a quick walk around in this half hour. And then as we circle back, we'll end up over here on the laser cutter, where we will be uploading your designs and making them today. Okay, so at the end of this session, by about 4 o'clock Dubai time, we'll have a camera mounted on that machine there as it progresses through and as it is showing off all of your designs in real time being manufactured. So you'll be able to tune into that later, well, from 4 o'clock. Okay, so with that, let's take a quick look at your design. There's still a little bit of time if you haven't already to upload your design, so please do that. There isn't much time, but if you have time, please prioritize that. So what we're going to look at first, though, is some of the designs that you made. So we might be able to put them up on the screen here, or it should be appearing on your screen at the same time. Okay, so you should be able to recognize some of your own drawings here. Really inventive. I really like them. I hope, from what I understand here, as not a manufacturing, you've gone with different shapes on the outside. The black, again, just to refresh, Mohammed, the black means it's going to be cut through. And effectively, that's telling the laser cutter there to be stronger, as in to be more powerful, and also perhaps a little slower, right? And so it's concentrating more energy and then cutting through the perspex. Whereas the blue here, I'm not going to try. Somebody want to help pronounce? No? No. I'm going to take Tanzim's. The blue there is going to be a bit faster and lower power, so it's going to etch that out, giving a nice image to it. So we'll get back to this later, and we'll take a look at these happening in real time. Okay, so as I said, we had a little bit of problem this morning. I think some of you weren't able to see our YouTube live, so we're going to continue on our teams here to go around some of our manufacturing technology. Rest assured, pretty much all of these sessions have been recorded, and we'll later today or tomorrow, we'll provide you with links to the different sessions if you wanted to review them. There's just a private YouTube link for you to see maybe some of the tuition that you got in design today, maybe some of the YouTube live that we're going to have of the design process, or maybe just some of the informal introduction to design principles that we had, and obviously this session too. So if you've missed anything, or if you want to share with friends at a later stage, please feel free to do so. Okay, so let's take a walk around. I'm going to put my mask on for this because I'm going to be talking to Mohammed, and we will kick off in our workshop. So please follow me. I'm making perfect and run circles. Thank you. As we walk into our workshop. So the workshop here is just one of our workshops. Today, health and safety, obviously always very important to us. Today, it's not a working workshop, but we have health and safety as a huge priority for us. It's about how we dress as well as how we act in a particular area, and very important to engineers. So if we go down here, one thing we're really keen to discuss and to demonstrate, Rebecca, is robotics, and the role robotics can have in manufacture, right? So we have courses in robotics, autonomous interactive systems, electronics, electrical, and all that, not always associated necessarily with manufacture. So can you tell us why robotics are important to manufacture then?
Yeah, well, robotics come to the manufacturer whenever you want to be having very accurate result on a task which repeat over and over. Take, for example, welding a joint, and then you have thousands of that joint where you will need every time to weld with the same precision and then the shield of material. That's not only it. Robotics now coming almost in every field. There are high accuracy robotics, which is even used in surgeries, remote control, military, space, and you name it. But the key for manufacturing, which is our core today, is really to save you time.
Yeah.
They can work over continuous number of hours, improved accuracy, of course, and then the repeatability, which is very important here.
Okay, so can we take a quick look at some of our robots? I'll let you go first.
Yeah, so here we got a couple of arms or manipulators. So I'm trying to program the left one here, the motor man, to do our small welding joint.
Okay.
So I'm going to activate it now, and you will see it's coming from that position, which was doing something else with the ADB robot. And then it will keep going through that joint over and over. So let's give it a try.
Okay, so I'm going to narrate from here. You can look at the robots there. So this robot here, it's big, it's chunky, it's cumbersome, but it's also very fast, and importantly, it's very, very precise. So what you're able to do here, I think I'm right, Mohammed, is you can have an attachment on the end. In this case, you're talking about having a welding iron, something that is going to repeat the exact same manufacturing process over and over again. We're talking like way sub-millimeter accuracy, aren't we, and repeatability. So if it was to do this 10,000 times, you're going to be within that millimeter on the 10,000 ones as you were the first one. And that is so important for us in manufacture, because when you're talking about large-scale manufacture, precision is what it's all about.
Yeah,
okay.
That's exactly it.
We'll just scan through. I know we're moving into obviously a new kind of very impressive state-of-the-art campus, right, from January 2021. But some of the more traditional practices will still exist, right? We're still going to have a tool shop, where we learn the fundamentals about manufacture. So simple things like, what do we have here? Just like battery-powered drills, vice grips. Some of the very simple stuff will still exist in the new space-age type campus that we're going to have, right?
This is really important because getting the basics right is very important. Engineers are often going to lead. They're going to manage a team of technicians, allocate tasks. It's really important for them to know how things are done.
Right.
It's important for the engineer to have hands-on welding, but it's not his job to be a welder,
right.
Or her job, of course. That applies to using machine tools, lathe, turning machines, and milling. So it's gathering all these basics, getting it to the next level with the computer-aided design and manufacture, and then get it to the managerial level, which is expected from engineers to manage all this.
So to summarize a bit of what you say, you're saying, well, undergraduate students, they learn about all these techniques, they experience them, they use them, but they're not intended to become master craftsmen or mechanics necessarily, but enough so they know when they're designing something, they want to know, well, am I designing not just for the product and the function, but I'm designing for how I might manufacture them? Because making one is one way of manufacturing. Making 10,000 per hour, perhaps, then you have to know about the different types of manufacturing, that what goes into it.
Yeah, and there is lots of planning actually goes to that. Whenever you start with the design, which is probably the bit which you covered early in the morning today, then you move from that to prototyping and then get to your process planning, where you think about how you are going to get the raw material, where you will store it, how you will feed it to the manufacturing line. And then robots or human will be dealing together to come up with your finished product until it's packed and get to your end user.
And something we did discuss this morning in design was it's not just about, efficiency, or it's also about, material use and that's kind of sustainability. So that when you're making, say you are making 10,000, and if you manage to save a small fraction of material, or I don't know, 10 seconds on each individual, that sums up to a lot of time saving, a lot of material saving, and a lot of cost saving, right? So that's kind of, all of those factor into the design process. And it's not always immediately obvious that when we're designing something, perhaps like you were doing today, that you're in the drawing mode. You're not necessarily in the full design process mode. Okay, cool. Can I, seeing as we've said so much about welding, can we take a quick look inside the welding bay?
Yeah. Please.
Right, so you lead on and I'll follow after.
So this is our welding bay in here, and everything related to metal will be done in this space. We will need, obviously, to have a special extraction. That's why we separate everything in this room.
Well, can I start even easier than that? Welding effectively is a thermal process, right? So you are putting a lot of heat into one area. Depending on the type of welding you're doing, sometimes you're just melting the material, the metal, and then bonding. And sometimes you're adding metal into it. And sometimes you're doing it with electricity, or gas,
you
right?
need to have the metal reach a point where it's liquid.
Right.
So you will need to heat it up most of the time.
Right.
How you do that heating, this will be based on the welding technique you are using. And the trick is some metals, they don't like to be melted.
No.
Like aluminium, for example.
And they don't like to be cooled.
Yeah. So you will need to shield them out with it. Inert gas, for example, argon, and separate them from O2 to avoid oxidization and then weld together. So for this, different technologies are used: gas welding, TIG, MIG, where you will have to insert metal or tungsten and so on. And we do cover all that in this welding bay. Again, students, they get hands-on, where they will, as part of their course, do welding, but they are not expected to be welders at the end of the day.
And one of the biggest projects I've seen go through this relatively small welding bay is the frame of the Formula Student car. So for those who don't know, Formula Student, it's a competition to design and build a Formula One style car. I'm wearing the livery here on my back today. But it's based essentially on a chassis or an airframe, which essentially is just a bunch of tubes that have been sort of bent, but also cut and then welded together to create this frame where you put everything else, right? You put on your drivetrain, you put on your suspension, you put on the wheels. Essentially, everything hangs on that airframe. So it's probably the most important component that's there. But it's fantastically complicated as well because it's made out of, what would you say, maybe 40, 50 parts?
At least, yeah.
And they all just need to sit together and then need to be, well, I know we tack weld first.
It's very precise because all other components will fit in or on that chassis.
Right.
So it starts pretty much where you guys started today, with the computer-aided design.
Right.
Where then that develops a little bit to go into a simulation environment, where we will need to identify the weak points or if there is any fault with the design or expected failure points, and then take it to the manufacturer. And then here you can, of course, use a manual.
And that brings us back to the kind of the robotics we had earlier, right? Because the robotics themselves, there's, sometimes it's the weld that might be the weakest part, and it comes down to the skill, would you say, of the individual welder, how practiced they are, how experienced they are. Whereas if you're doing it with a robot, you can pretty much have a lot more confidence in the quality of the weld and establish that it won't be the weak point anymore, which is obviously very important to us when we're designing something.
That's absolutely right. And today's robotics can interact with the accessories, for example, the welding machine, to set variables within that, like the current, the voltage, and so on, to make sure that it actually gets the perfect weld every time and every joint. And that is really critical for chassis because it feeds directly to the safety and the test with the car go through and the competition.
Excellent. Good stuff. Okay, let's leave the workshop and go back into our innovation hub kind of makerspace area, because to a certain extent, we'll just talk as we walk. To a certain extent, I always considered this kind of workshop to be the more traditional engineering manufacturer. It's the tool shop, it's the welding. These have existed for a long period of time. Whereas manufacturers move forward, not just in the kind of the approach to it, but in the different types of manufacturing process we have here. Many people will be familiar already with, what we call rapid prototyping. And when we think about rapid prototyping, we probably think more about 3D printing, whereas rapid prototyping is, well, it's a range of different techniques that develop things quite quickly. And to a certain extent, I even think of these CNC machines. CNC, by the way, stands for computer numerically controlled machines, as kind of rapid for me, because what do? I take a billet,
Yeah.
like a cylinder of what is that? Some sort of plastic, or
Yeah.
and we place it in something here, which we call a chuck. So that just holds it in place there. And then we have these tools that we can select. Now, this chuck here spins it quite rapidly, doesn't it? Can you give us this gets a bit noisy, but
Yeah.
it's worth a look. So this is going to spin.
So basically, we got our workpiece right in the middle and there, and we do have a selection of tools on there which we can change. I'm just going to select a tool which is good for facing, so you can see. Now this automatically happens. I'm now overriding that manually just to show you. But in reality, you will come with the complete design, feed it into the machine, and that's it. You will be really good to go.
So we spin the tool up to a really high speed. You were saying up to 1400 RPM? And then we move the cutter, the tool, into the surface there. And oh wow. And it just really quickly takes a cut or a slice.
And then it can also form shapes.
Oh, so you took a step into it there?
Yeah.
Wow.
See what we got.
Now, to me, that still classes as rapid prototyping because that's pretty quick.
You will end up with a really good finish.
So all this stuff is just the waste material.
Yeah.
In metal terms, I call it swarf. Do we still call it in plastic? Is it still swarf?
Yeah, it's material extract, and normally in the manufacturing line, you will worry about these.
Right.
How do you recycle them? How to reduce them?
Yeah.
Because this is cost.
And that's waste.
And it's waste.
Absolutely.
Yeah.
Excellent. Thanks very much. So that there is called a lathe, and the process we call turning, for obvious reasons. Over here, we have milling machine. Now, to he who's not an expert in manufacturing, I consider this to be a drill that can go sideways. So a drill to me normally is about going straight through, cutting a hole, right?
Yeah.
And maybe putting a bolt through it or something. Here we have a drill that is able to move sideways and to translate a pathway. So maybe you could show us, here's the example, right? So this is your simulation of the drill, and it goes into the machine. Yeah, it goes into the, not the machine, into the blank, the block.
We just move it step by step. We do see the coding in here, which we call a G code. But for today's interest, you would see the tool coming, approaching the material, and then getting in and then start a cut. And that will cut all the way based on the code, and then just continue doing that in multiple lines to follow the design.
So this is a drill, though, that's going around at a speed, right? So it's still going around at hundreds of times per minute.
Yeah.
And then you have another speed, which is its translation speed. And it's following a pathway. Yeah. Right, okay. Cool, and that's what you end up with. I don't think we have time to demo this.
Yeah, but we can just show how basically the bed moves in here.
Oh, so in this case, the bed moves.
Yeah,
and
the tool is fixed. It can go only on Z direction, up and down, but X, Y will be on the bed. What is interesting about this machine as well, it got like tools, tiny tools, pretty much like what you would see in a dentist.
Oh, wow, yeah.
And you can use these to manufacture circuit boards.
Just so you know, I never want to see one of those in a dentist.
Yeah.
But yeah, what I just happened to pick up there is that this can be applied not just to complicated material. This could be like a PCB, a printed circuit board, essentially, which for your electrical or electronic design. That's quite cool. I like that a lot. Okay, so let's move on a little bit to the 3D printing elements. So we had this running earlier. It's not running now. But I want to describe a little bit about, we've probably heard of 3D printing before. Maybe that's what we think rapid prototyping is. For me, it's additive layer manufacture, ALM. It's where you put one layer on top of another. So it starts with a raw material. Again, this kind of plastic that's on a stool, and we kind of push it through like as a hard plastic the whole way through until we get to this nib here. Now this nib will be at up to 210, was it? 210 degrees Celsius. And that's where the plastic becomes molten, or where it becomes very soft, even liquid, you might say. And we place it down layer on layer, kind of like toothpaste coming from a tube, as you can imagine, drawing it over and back. So the work that we do as engineers is programming that pathway. So what path is it going to follow as it layers down layer upon layer upon layer? And you can end up with some quite nice objects just like this, right? So that was all 3D printed in a few hours. And the one I just saw today is obviously the Burj Khalifa. There's a small scale replica, just in case anybody is wondering. I'm not some sort of giant. And we've used it obviously to generate, this vehicle here, and we're able to put in a wind tunnel. We're able to determine whether this front end is giving us the right downforce, or the reducing drag, or whatever we want to do. We can kind of create this prototype quite quickly, test it, and then see if our theory is working before we go to the kind of the investment in full-scale manufacture. And by investment, I'm always thinking not just about money. I'm thinking about the time, the effort, the material, all that goes into the full-scale investment. So I think we have a couple of minutes yet where we can look at this bender. Will we look at this bender? So this is a fun thing to look at. Essentially, again, it's a thermal process where we've taken a little bit of this acrylic, I'm going to say, and what we're doing is we're heating it up on that red line. And what you told me earlier was that the either side of the red line are actually coolers.
Yeah.
So it's maintaining a thermal gradient. So you end up with a very hot spot or a hot line, and then you have the cooler areas there. The idea being that what happens at the bend? It becomes really soft.
It becomes really soft and allow the material to deform without reaching that, plastic, and it breaks down.
Right.
You can also decide on the angle you want to bend it at using the form in here.
So I realize this is one you made earlier.
Yeah.
So, and we'll make one now in a second. This is a flat just like that. And this is one that we made today. Now, obviously this is a hard plastic. If I was to bend this, I'm just going to snap it. And it's going to go. So whereas what you're able to do here is heat it up, bend it into the shape you want it to be in, and then when it cools down, it'll want to stay there.
Exactly. And this gets really useful if you want to, say, make a frame or convert basically a sheet of flat design to something in 3D.
Yeah.
You can always think about the 2D design, which we do, cut it out and do it.
So I can only imagine how complicated that would be if I made it out of, 1, 2, 3, 4, 5, 6 shapes. How do you stick that together? Are you welding it together, or are you bolting it together? It's all those components, whereas this essentially is cut out once and then just bent into shape. Much better. So how are we doing now? Do we think we're ready to go?
Well, almost, I think. Just a little bit.
Just not there yet?
Almost. So this basically run a line of a heater in there, and you can see it glowing. We can adjust actually how wide or narrow this can be.
Which would have something to do with the radius.
Some bends will be at a higher radius, some of them will be not.
And maybe also the thickness of the material.
Yeah, that's it too.
Excellent.
So this will take us a second, and we should be really good to go. And I can see now it's already sort of getting software.
So the idea of plastics, obviously.
Really hot, so protection is really important here.
The idea of plastics, of course, is that they generally are poor conductors of heat. So this is a relatively slow process. We have to be patient, I guess, to make sure it gets to the temperature slowly so that it can focus that melting point. Okay, cool.
Let's do it.
So now it's hot. You're just going to bend it and then fit it.
And then fit it right into there.
So this is an angle that you said earlier.
Yeah.
To the angle that you want it to be. I guess at this stage, it's going to, this is the quick bit.
Yeah, then now that is done.
Excellent.
So we started from a flat, we got it standing like that. And this can be cool on the keyboard we are doing today.
Indeed.
Maybe like melting down and falling on the table.
Okay. So the final one I think we're going to take a look at, well, I say final, I mean second to final, because we're going to conclude today by looking at the laser cutting your designs. But so just before we get to that, we have one more. This is a fun one for me because this one is called vacuum forming. And Mohammed's setting it up there nicely. Essentially, it is a thin, relatively thin piece of plastic that we're going to heat up. We're going to pull it down on top of a mold. So what the mold could look something like this, maybe some sort of shape that we're trying to create. I think you have one over there as well. We're going to pull it down on that when it's nice and hot. So it's just going to be really, really loose, just like that.
And you probably ask, why would I do a form of something I already have? Now, this gets really useful if you can 3D print something, but this is not the final material you want to use.
Right.
So you can then make a form.
So this becomes the mold.
And then you can get any material
for like jelly shots or something.
Or chocolate.
Or chocolate.
Even
or
you
soap,
can make a sand mold for metal from that. So this is heating up. It's going to take a minute, and we are going to choose something in. It's important that whatever you put in, you should be able to take it out.
Yeah.
So that will look.
So you wouldn't put a ball in there.
I'll put this in, and let's see what we end up with.
So
there is a mesh there, and that is connected to a vacuum source at the back, and that will be evacuating all the air and basically just forming that plastic tie on our.
A little bit like vacuum packing your clothes in a before you go. So it's making some noise now. Does that mean it's getting up to temperature?
Yeah, we are good to go now.
So this can happen quite quickly. So straight down, vacuum on. And is it cooling as it goes as well?
Yeah, and then keeping it straight.
All done.
And then we are good to take it out. We started, by the way, by a plastic sheet, just a thin sheet.
A thin sheet.
And this is still.
That's very quick because it really cooled down and
so what do you think is this?
What of it? Awesome.
What do you guys think I made just now?
I think you made it look easy. Okay, I didn't know that's what it was. All right, awesome. Okay, so that's really cool. I know there's so much more we can show you in these labs. There's a lot that we haven't shown you in terms of electronic design. How do we, Arduino Raspberry Pis, how these smart, cheap electronics that we integrate into our mechanical systems to make them work. There's so much more we could show you. We just don't have the time today. What we want to move to now is the manufacture of your design. So we're going to take a few minutes as we're getting up to 4 o'clock Dubai time to show you the setup of your designs. And then we'll invite you afterwards to just keep track of them on the YouTube link. Yeah, the YouTube link that you've all been provided with after that. It'll take a bit of time to laser cut and scan or to etch each one of yours. So we'll leave you to watch that in your own time. But we'll start with the setup. So Musin, you want to show us what you're doing here?
Exactly. So I've imported their designs, the one they have sent to us. And I've arranged in a way that represents the bed of the laser cutter.
Okay, so this is your first batch of 10.
Yes.
Great.
Yes.
And you've just uploaded it to the machine here. Does it appear up here then?
No, we are sending directly to the machine, like live feed rather than downloading to the machine.
Okay,
but
no problem.
Yeah.
So can we see the first one start?
Yeah, sure.
So that's a laser over in the back left. It's moving in. And it's starting to scan already. So let's see if we can recognize some of that. The camera can't get too close because this is a laser process, and it's actually laser that we can't see. It's outside the visual range of wavelengths. But it is high power, and you can see what it's doing. It's making these marks on the surface there. Okay, so how long do we think these 10 are going to take? Yes, first batch?
15 minutes per batch.
15 minutes. Oh, that's still quite quick, isn't it? Okay.
That's what our numbers here.
Excellent. Okay, well, it's just at 4 o'clock. We're sticklers for time here, so we're going to try and leave you at that. I hope you've had an absolutely amazing day. It's been really gratifying for us to see your level of engagement and to see your designs that you've created. We're very excited to see these now as well. There'll be a certificate and all that winging its way to you, and we're going to make sure that we also get a link, a hyperlink to all of these recordings if you want to review any of them later. But we'll leave you at that. Maybe leave it 2 minutes for us to set up, and you'll be able to watch your designs come to life live on YouTube in the next couple of minutes. So again, thanks very much. If there's anything else that you want to do or ask us about, let us know. Watch this space for other design engineers or other engineer for a day for different disciplines. And we will hope to do a lot more. So from now, thank you from me. Good luck. Listen, you want to say hello, goodbye?
Thank you.
And Mohammed, thank you to the team here. They've done a great job. And best of luck. And yeah, hope you have a great engineering career and future ahead of you. All right. Bye, guys.